Right now, sitting inside the device you are using to listen to this is a microscopic chemical pressure vessel.
Yeah, it's basically a tiny liquid-filled metal can that is, slowly and inevitably evaporating.
Exactly. And if it gets too hot, it dies faster. Plus, if you were to somehow open your device and plug that tiny cylinder in backward, it would literally explode.
Which is wild to think about.
It really is. So today, we are cracking open the hidden, highly volatile world of the electrolytic capacitor.
It's just entirely invisible to most people, yet our entire modern infrastructure is completely dependent on the electrochemistry happening inside those tiny metal cans.
Totally. And our mission today is to figure out why. Our source material for this deep dive is a massive, incredibly comprehensive Wikipedia article simply titled Electrolytic Capacitors.
It's dense,
Yeah.
but there is so much good stuff in there.
Oh, for sure. Okay,
Well,
let's unpack this. Why should you, the listener, care about a tiny cylinder soldered to a motherboard?
well, without them, nothing works.
Right. These components are the sole reason our gadgets can store the energy needed to be so incredibly small and fast. But, as we will see, they are also delicate chemical bombs that have literally caused global tech meltdowns.
What's fascinating here is that this isn't just a story of modern cutting-edge tech. I mean, the foundational science for this component stretches all the way back to the 1850s.
Wait, the 1850s?
Yeah, exactly. We are relying on the bizarre, almost magical quirks of a few specific metals discovered back then to keep the internet running today.
That is insane. But before we get to the explosions and the 1850s science experiments, we need to understand the physical reality of what this thing actually is.
Right, like how do you pack so much electricity into such a ridiculously tiny space?
Exactly. At its most basic level, a capacitor's job is just to store electrical energy. It is a polarized component, meaning it has a positive side, the anode, and a negative side, the cathode.
And between those two sides, you have the dielectric. You can kind of think of the dielectric like a microscopic, impenetrable rubber wall separating two powerful magnets.
Okay, I like that visual.
Yeah, so the positive and negative charges desperately want to reach each other, but the wall stops them. So the energy just sits there, stored in that tension, waiting to be released when the circuit needs it.
And in a standard old-school capacitor, you might use like a physical sheet of ceramic or plastic film to act as that wall between the positive and negative plates.
Exactly. But an electrolytic capacitor throws the plastic sheet out the window.
Right. The positive plate is made of a very specific type of metal. When the manufacturer dunks that metal into a chemical bath and applies a voltage, the metal literally grows a microscopic layer of rust over its surface.
An oxide layer, technically.
Yeah, an oxide layer. And that layer of rust basically becomes the impenetrable rubber wall. It becomes the insulator.
And because it is grown chemically through a controlled reaction, that oxide layer is unbelievably thin. We are talking nanometers.
Which is mind-blowing.
It really is.
Yeah.
And the thinner the wall, the stronger the attraction between the positive and negative charges, and the more energy you can store.
But the real secret to their massive power capacity is the surface area of the metal itself, right?
Yes, exactly.
Yeah.
The volumetric efficiency, or CV product, relies heavily on that surface area.
I want you to picture a standard flat sheet of printer paper. If you lay it on a desk, it takes up a specific footprint.
Right, like 8.5 by 11 inches.
Yeah. Now, take that same piece of paper and tightly crumple it up into a tiny ball. That crumpled ball takes up a fraction of the space, but the actual physical surface area of the paper hasn't changed.
Which is a great analogy because manufacturers do exactly this to the metal inside these capacitors.
They microscopic crumple it.
Basically, yeah. Through chemical processes called electrochemical etching or sintering, they eat away at the flat metal until the surface is incredibly rough and porous.
So if you look at it under an electron microscope, it looks like a jagged microscopic sponge.
Exactly. And by microscopic crumpling the metal like that, they can fit up to 200 times more surface area into the exact same volume.
Wow. 200 times. So in the world of energy storage, more surface area combined with an incredibly thin insulator equals an enormous capacity to hold an electrical charge.
Right. But to make that crumpled surface actually work presents a massive engineering hurdle.
Because it's so jagged.
Yeah, you have this jagged, microscopic mountain range of oxidized metal acting as your positive plate. You need to get the negative plate, the cathode, to perfectly touch every single microscopic nook, cranny and valley of that rough sponge.
Which you obviously can't do by just pressing another flat piece of solid metal against it.
No, it would only touch the highest peaks and completely miss all the valleys.
So the engineering workaround here is just brilliant. The cathode isn't a solid piece of metal at all. It is the electrolyte itself.
Yeah, it's a conductive liquid, a gel, or even a solid polymer that flows entirely into the sponge.
Yeah.
Perfectly molds to that complex microscopic surface.
So the liquid physically becomes the negative half of the component.
Exactly. And there's another deeply elegant detail about the manufacturing process. The voltage the factory applies during that initial chemical bath literally dictates the thickness of the oxide layer.
Wait, really? It's that precise?
Yeah. If they want a capacitor rated for 10 volts, they apply a little over 10 volts. And the rust grows exactly to the thickness needed to hold back that specific pressure.
That is so cool. They basically custom grow the insulation atom by atom.
They do. But you can't just use any random metal you have lying around to achieve that perfect uniform layer of rust.
Right, you need specific materials that behave in very strange ways under electrical pressure. Enter the valve metals.
Yeah, early researchers coined the term valve metals because these specific elements form an oxide layer that behaves physically like a one-way gate for electrons.
Meaning it blocks electrical current from flowing in one direction, but allows it to flow freely in the other.
Exactly, just like a physical valve in a plumbing system. And the three main families we utilize for this are aluminum, tantalum, and niobium.
Which brings us back to the history. The source notes that a German physicist named Johann Buff first documented this weird one-way valve cork in aluminum way back in 1857.
Yeah, 1857. And then, fast forward to 1896, and Charles Pollack realizes that this oxide layer stays perfectly stable even after you turn the power off.
So he patents the first liquid capacitor based on this chemistry.
Right, and that patent basically laid the groundwork for the very first industrial applications.
Which were pretty clunky at first. In the early 1900s, early telephone exchanges were plagued by massive audio noise issues on their power lines.
Oh, the static must have been terrible.
Yeah, so to filter out that electrical static, engineers built the very first wet aluminum electrolytic capacitors, but calling them components feels like a huge stretch.
Oh yeah, they were massive. We're talking about literal jars or heavy metallic boxes filled with a sloshing solution of borax and water.
With just a folded aluminum plate dropped inside. Imagine trying to run a telecommunications network where your power filters are essentially giant, open buckets of chemical water.
It's honestly hilarious. They were heavy, prone to spilling, and entirely impractical for anything moving or consumer-facing.
Right. So the shift to modern electronics required getting rid of the sloshing jar. In 1925, an inventor named Samuel Rubin teamed up with Philip Mallory.
Who was the founder of the company that would eventually become Duracell, actually.
Exactly. And Rubin invented the dry aluminum capacitor, though dry is a bit of a relative term here.
True, it isn't bone dry. Rubin basically took two long, thin strips of aluminum foil and separated them with a highly porous paper spacer.
Then he soaked that paper in a thick, non-aqueous chemical paste, which is the electrolyte.
Yeah, and then he rolled the whole sandwich up tightly into a small cylinder and sealed it in a metal can. Suddenly, you have a compact stacked component that doesn't leak when you tilt it.
And that specific invention is what made early, affordable home radios possible. But the real evolutionary leap happened in the 1950s, entirely driven by the transistor revolution.
Right, because William Shockley and the team at Bell Labs had just invented the transistor.
And transistors were microscopic compared to the old vacuum tubes they replaced. But the aluminum capacitors needed to support those transistors were still comparatively bulky.
So Bell Labs had to figure out a way to shrink the energy storage to match the tiny new switches. They abandoned aluminum and turned to tantalum.
Right. In 1950, researchers took pure tantalum powder, pressed it into a tiny pill shape, and baked it at roughly 2,000 degrees Celsius in a vacuum.
Which is that sintering process we mentioned earlier.
Yeah.
It fused the powder into a highly porous, solid metal sponge that was incredibly dense with surface area.
But they still had the liquid problem, didn't they? They had this amazing new solid sponge, but they were still soaking it in liquid electrolytes.
Yeah, which wasn't ideal for the new era of pristine solid-state electronics. But by 1952, Bell Labs cracked it. They figured out how to use manganese dioxide as a completely solid electrolyte.
Wow. So they created a capacitor with no liquid paste, no evaporation, and insanely high reliability.
All shrunk down to a fraction of the size of an aluminum can.
Okay, I need to stop here because logic dictates that if Bell Labs figured out how to make a leak-proof, highly conductive, incredibly reliable, completely solid capacitor in the
The
1950s.
liquid-filled aluminum one should have gone extinct.
Yes, exactly. Yet the source material states that today, the vast majority of consumer electronics still rely on wet, non-solid aluminum electrolytic capacitors. Why are we still putting liquid paste inside our modern flat-screen TVs?
If we connect this to the bigger picture, engineering is always a brutal compromise between physics and economics.
Hmm.
First off, aluminum is one of the most abundant elements on Earth. It is incredibly cheap.
Whereas tantalum is rare, right?
Yeah, its extraction is complex and its global market price is highly volatile. So we use aluminum because it keeps the cost of a laptop charger under 50 bucks.
Makes sense.
But cost is just the primary driver. Wet aluminum capacitors also possess a massive technological advantage when dealing with the messy, unpredictable reality of city power grids.
They can handle power surges better.
Exactly. They are remarkably resilient to sudden voltage spikes. If a rogue surge of electricity hits a wet aluminum capacitor, it acts a bit like a pressure relief valve on a steam pipe.
Oh, so it briefly lets a little current leak through the oxide layer, safely absorbing the blow, and then the chemistry seals itself right back up.
Yes. Whereas the solid tantalum,
Let me guess, they don't handle surges well.
not at all. Solid tantalum capacitors are incredibly reliable under perfect conditions, but they have zero tolerance for electrical abuse.
Yikes.
If they get hit with a sudden high-energy voltage spike, the solid dielectric shatters. It creates a dead short circuit.
And because the solid manganese dioxide electrolyte contains oxygen,
The massive heat from the short circuit can literally cause the component to ignite and aggressively burn right on the circuit board.
so we essentially trade the risk of a literal miniature fire for a cheaper component that can handle a bit of rough electrical weather.
Basically, yeah.
But because we are forced by economics to put these wet aluminum capacitors into nearly every device we own, we have to deal with their fatal flaw. The liquid is trying to escape.
They really are ticking clocks. To understand why they inevitably die, we have to look at how they operate in a circuit.
Because they aren't just sitting there holding a static charge, right?
Right. They are constantly, rapidly charging and discharging to smooth out the flow of electricity. This alternating current flowing in and out is called ripple current.
But nothing in the physical world is perfectly efficient. The materials inside the capacitor have a natural resistance to that constant flow of electricity.
Engineers call this equivalent series resistance, or ESR.
And when the ripple current pushes through the materials, that internal resistance generates physical friction. And friction generates heat.
Which is the absolute enemy of the liquid electrolyte.
Think of it like the oil in your car engine. The ripple current is the friction of the moving pistons. The ESR determines how severe that friction is.
And the heat generated by that friction slowly, relentlessly boils off the engine oil.
Exactly. Inside the capacitor, the liquid electrolyte is the oil. As it gets hot, the liquid turns into a gas and slowly pushes its way out through the rubber seals at the bottom of the tiny metal can.
And as that liquid evaporates, the internal resistance of the capacitor actually goes up.
So higher resistance creates even more heat, which evaporates even more liquid. It is a vicious, accelerating cycle.
Yep. Eventually, the capacitor simply dries out, loses its ability to store energy, and the device it powers refuses to turn on.
You know, this makes me think of how companies like Apple will sometimes design incredibly thin laptops with minimal venting.
Oh, basically gluing the aluminum chassis shut.
Yeah. They prioritize silence and sleekness, but they are trapping the internal heat. They aren't just making the computer run warm, they are literally evaporating the lifespan of their own internal component.
Which is absolutely true. Engineers actually map this life cycle out mathematically using the bathtub curve.
The bathtub curve.
Yeah, if you graph the failure rate of millions of components, it looks like a bathtub. You have a steep drop at the very beginning. Those are the units that fail immediately due to factory defects.
Okay, then what?
Then the curve flattens out into a long, stable plateau. That is the reliable working life of the device. But eventually, with wet aluminum capacitors, you reach the other end of the bathtub.
Where the curve spikes sharply upward again.
Exactly. That is the unavoidable wear-out phase, where the liquid has simply evaporated away.
And the speed at which you hit that wall is governed by a physical law called the Arrhenius rule, which engineers casually refer to as the 10-degree rule.
It is a stark reminder of how heat accelerates chemical reactions. I mean, heat is just atomic motion.
So the hotter the liquid inside the capacitor gets, the faster its molecules vibrate, and the faster they push their way past the rubber seals.
Right. The rule states that for every 10 degrees Celsius you drop the operating temperature, the lifetime of the capacitor literally doubles.
That is massive. So if a capacitor is rated to survive for 2,000 hours at a boiling 105 degrees Celsius, and you instead run it at a comfortable, well-ventilated 45 degrees Celsius,
You double that lifespan, 6 times over.
that measly 2,000 hours mathematically scales to over 128,000 hours. You can take a component destined to die in a few months and make it last 15 years, purely by keeping it cool.
It perfectly demonstrates why thermal management is the most critical aspect of modern electronics design. Interestingly, there is also a truly bizarre chemical quirk to how these oxide layers age when they aren't subjected to heat.
You mean when they are just sitting completely unused?
Yeah.
Oh, the self-healing phenomenon.
Exactly. If you take a wet aluminum capacitor and leave it sitting in a drawer for 5 years with no power running through it, the chemical aggressiveness of the electrolyte paste will slowly start to eat away at its own delicate oxide layer.
So the internal rubber wall starts to rot and thin out.
Right. And if you were to pull it out of that drawer and immediately slam it with full power, that weakened wall would shatter, causing a short circuit.
But if you apply a positive voltage very, very slowly, like just a gentle trickle of electricity,
The capacitor will use that current to trigger the original electrochemical reaction. The electricity physically pulls the oxygen atoms out of the liquid and bonds them to the bare aluminum.
regrowing the oxide molecules and patching the microscopic cracks in the wall while it sits right there in the circuit.
Yeah. The electricity literally rebuilds the rust barrier.
It is a self-repairing mechanism built into the physics of the metal. That's incredible.
It is. But, as we established early on, they don't always quietly dry out, and they don't always peacefully heal themselves. Sometimes the pressure vessel violently fails.
Because we cannot ignore the physical reality that these are sealed metal cans containing highly reactive chemistry. So what actually triggers a catastrophic failure?
Gas. It always comes down to gas.
Like from a power surge.
Yeah. For instance, if a power surge subjects the capacitor to severe overvoltage, pushing vastly more electrical pressure into it than the thin oxide layer was grown to handle, the current spikes, generating massive instantaneous heat.
And then the liquid electrolyte rapidly decomposes into hydrogen gas.
Exactly. Hydrogen gas rapidly expanding inside a sealed, rigid metal cylinder.
That sounds bad.
It is. The internal pressure builds exponentially until the aluminum casing simply bursts open. The same exact physical mechanism happens with thermal runaway, where the ripple current generates heat faster than the surrounding air can cool it.
But the absolute fastest way to detonate one of these is reverse polarity, right?
Well, absolutely.
Hmm.
Because, like we established, valve metals act as a one-way physical gate for electrons. The oxide layer is literally designed to block current flowing in one specific direction.
So if a manufacturer accidentally solders a capacitor onto a board backward, connecting the positive voltage to the negative terminal,
The electricity violently attacks the oxide layer. It rips the microscopic wall apart almost instantly.
and with the barrier gone, you get an unrestricted, massive flow of current directly through the liquid electrolyte.
It boils into gas in milliseconds, the internal pressure spikes violently, and the casing detonates. It often fires the metal can into the air like a bullet and sprays boiling chemical fluid across the entire circuit board.
That is why every single electrolytic capacitor has a massive, brightly colored warning stripe painted down its side, pointing to the negative leg.
Yeah, you really don't want to get that backward.
But sometimes the explosion has nothing to do with heat or voltage spikes or someone plugging it in backward. Sometimes the component is doomed from the moment the chemicals are mixed.
Oh, yeah.
Here's where it gets really interesting. The source material details a massive, decade-long global crisis known as the capacitor plague.
It is a profound case study in how a single microscopic error in chemistry can scale up to bring down global infrastructure.
So in the late 1990s, researchers in Japan, specifically at a manufacturer called Rubicon, were trying to solve the internal resistance problem. They wanted to lower the ESR to reduce the friction and heat.
And they discovered that using a highly purified water-based electrolyte was incredibly effective.
Because water is remarkably cheap, it flows perfectly into the microscopic metal sponge, and it dramatically improved the electrical conductivity.
But water poses a severe chemical threat to aluminum. Left to its own devices, water will react aggressively with the aluminum anode, producing aluminum hydroxide and massive amounts of hydrogen gas.
Which means gas buildup. So, to prevent the capacitor from instantly destroying itself, the scientists had to formulate highly complex, closely guarded chemical stabilizers.
Basically, inhibitors that stop the water and aluminum from reacting.
Right. But then, through corporate espionage, a rogue scientist stole the baseline recipe for this highly conductive, water-based electrolyte.
Sounds like a movie plot.
It totally does. The thieves took the stolen formula and sold it to massive component manufacturing plants in Taiwan. These factories immediately began pumping out millions of these incredibly cheap, high-performance capacitors, selling them to every major tech brand on the planet.
But the thieves made a catastrophic oversight.
The stolen formula was incomplete.
Exactly. They managed to copy the water base, but they completely missed the proprietary chemical stabilizers. They were essentially building tiny, sealed bombs.
This raises an important question about the extreme fragility and interconnectedness of our global supply chains.
It really does, because that incomplete, highly volatile chemical formula was replicated and soldered onto millions of motherboards, power supplies, and the network switches worldwide.
And when consumers brought these computers home and turned them on, the unstabilized water inside the capacitors immediately began reacting with the aluminum.
But it was a slow burn. It took about a year or two for the hydrogen gas pressure to build up inside the cans.
And then, around the early 2000s, the tech world started popping.
Literally.
Dell, HP, Apple, networking giants, no one was immune because they all unknowingly sourced their base components from the same compromised factories. Thousands of network servers crashed. Millions of home computers simply refused to boot.
Motherboards were found covered in hardened, leaked electrolyte fluid, with the tops of the capacitors blown completely open.
It perfectly illustrates how deeply reliant our macro-level digital society is on invisible, highly precise microscopic chemistry. One missing ingredient in a chemical paste brought the hardware world to its knees.
Yeah, and it created an entire cottage industry of technicians who did nothing but painstakingly solder new, properly stabilized capacitors onto dead motherboards just to resurrect them.
So what does this all mean for you listening right now? I want you to just look around the room you are in.
Look at your TV screen, your laptop charger, the power brick for your phone, the router blinking in the corner.
Exactly. Every single one of those devices relies on the weird physics of valve metals and perfectly balanced electrochemistry. It is a direct, unbroken lineage of scientific iteration from Johann Buff's 1850s experiments to Samuel Rubin's paper rolls to Bell Labs, right to the gadgets sitting on your desk.
And every single one of those components is currently subject to the relentless laws of physics. They are all generating tiny amounts of internal friction, producing heat, and slowly evaporating their liquid lifespans.
So I want to leave you with a final thought to ponder that builds on everything we've explored today. We now know that these wet capacitors have a strict, heat-dependent lifetime.
Right, they have an eventual, mathematically unavoidable wear-out phase at the end of that bathtub curve.
Exactly. And right now, the entire world is aggressively transitioning to green energy infrastructure. We are filling our homes with smart meters, our driveways with electric vehicle chargers, and our global power grids with millions of massive solar inverters and wind turbine controllers.
We are deploying billions of new, highly complex electronic devices globally in a very condensed, rapid window of time.
Devices that universally rely on massive banks of electrolytic capacitors to manage that heavy electrical load. So what happens in 15 or 20 years when all those microscopic chemical clocks, deployed at the exact same time, hit the steep end of their bathtub curve simultaneously?
Food for thought.
Thank you for joining us on this deep dive. Till next time.